Hey, good afternoon, cohort B. I hope you're having a nice day at home. Let me show you where we are in the outline here today. We skipped over, here, let me skip this. We skipped over, we did the patterns. We're skipping over number 10. We're skipping over the quiz here. Forget that. We're going straight to number 11, okay, putting atoms together, ionic and covalent compounds. We're only doing lesson 11 today. That's all I did in class with the other group. Very important lesson though. Okay, so keep that in mind. I'm going to push some assignments, the assignment into your thing, the handout. It doesn't take very long. Okay, it's only takes like maybe 10 or 15 minutes to do it. They finished a lot of it in class today, so just to give you some sense of it. Okay, then we have a couple of labs coming up. Okay, that we'll sort of do together and write them up together. And then we'll get ready for our end of unit test. Okay, we'll go from there. All right then, so let's get straight to it. Putting atoms together, making compounds. Okay, so really it's what chemistry is mostly about, right? How atoms combine. Before we get into that, I don't think we talked about this yesterday, so let's just talk about this a little bit today. This was in the video yesterday, but I know that you were in class, but I don't think we really talked about it. So I want to talk to you about this just as a review. Number one, what is an ion? Pardon me, I biked in this morning, so just got a little stuff to clear my throat here. All right, so an atom or molecule that has gained or lost electrons. Now remember, electrons are the particles that are easy to gain and lose. Protons are in the nucleus, not so easy with those. Those are nuclear reactions, and those are quite energetic and quite difficult. Okay, it's not like it never happens, but normally it's electrons. Electrons are easy to add and subtract from something. Now, when atoms gain electrons, they become negative ions. Okay, they become ions. They gain electrons, and they're negatively charged. Those are called anions. Okay. If you lose electrons, I just want to say that here, the overall charge on the atom or molecule will be positive. I'll just highlight that in red, the positive charge, right? And these are called cations. So cations have a positive charge, okay? Anions have gained electrons and have a negative charge overall, okay? Now, remember what atoms are trying to do. They're trying to either fill their valence shell if you're a non-metal, or they're trying to empty it if you're a metal. Okay, so metals tend to form cations. Non-metals tend to form anions. Okay? Now, I have this assignment for you. What is an anion? An anion. I mentioned that in the video yesterday. Bonus mark if you can tell me what an anion is. Okay? All right, now I said this already, metals. Metals tend to lose their valence electrons and form cations. Non-metals tend to gain valence electrons to complete their shell, and they form anions. Okay? Now, a match made in heaven is this example of combining sodium. Okay, and sodium has one valence electron. Here, I'll color it blue. There's this little valence electron. And what it's going to do is it's going to donate that valence electron to chlorine. Now chlorine would like one more valence electron to complete its full octet, whereas sodium would like to get rid of it and expose the empty shell underneath. Okay? And like we said, atoms are more stable when they have a full outer shell exposed. So sodium does that by getting rid of an electron. That's what makes it a metal. Chlorine does that by gaining an electron, and that's what makes it a nonmetal and a halogen, okay, in this case. So what happens is there's a little donation that happens. So there's a little donation of an electron. Sodium is the donor, and it happily gives an electron to chlorine, and chlorine happily accepts it because it wants it. So it's a perfect match. It's a give and take relationship where sodium wants to give and chlorine wants to take, okay? Now, sodium will therefore form a cation, okay, that we call the sodium ion, and it now has a +1 charge because it lost one electron. But the chlorine, having gained this little electron right here, colored blue, having gained that guy from the sodium, it now has a negative charge, and this guy is an anion with a -1 charge because it gained one more negative charge. Okay, now we call the compound, the resulting compound, sodium chloride. So the anion, and this is key for today, the anion, we change the name. So I'll just underline it here. Instead of just calling it chlorine, okay, with the -1 charge, when chlorine gains an extra electron, it's now called the chloride ion, okay? And this forms a general category of compounds, like whenever we combine a metal and a non-metal like this, okay, in this case an alkali metal and a halogen, okay, they form this group of compounds that we call ionic salts. Okay, so table salt is sodium chloride, of course, and that's the one you eat. But there are other salts, like potassium fluoride is a salt. Okay, it's not table salt, and it tastes different. Okay, you might brush your teeth with the fluoride ion. Okay, it doesn't taste the same as the chlorine ion, but they still form, they're still part of a group of compounds that we call ionic salts. All right, so let's get now, that was something that was in the video from yesterday. So now you know what an ion is. Let's talk about ionic compounds. So how atoms combine, part 1. And as you can see, ionic compounds is the first thing we're going to discuss here. So here's the deal. We already know that metals like to give away electrons and form positive ions called cations. So we just told you that. Now the deal is, though, they have to lose all of their valence electrons, just the valence ones. Okay, remember, they don't lose all their electrons, period. They just lose the valence electrons. So, for example, sodium, okay, will lose 1 electron to empty its valence shell. But if we look at the periodic table here for a moment, okay, I included a periodic table in your in OneNote for you to use as a reference. Okay, so take a look. Here, lithium at the top, okay, is also an alkali metal. It would also like to lose 1 electron, and when it does that, it has a charge of +1. Notice the charge written in the top right-hand corner of the periodic table card. Sodium will also lose 1. Potassium, rubidium, cesium, francium, they all have a charge of +1 as they lose 1 valence electron to become stable. But beryllium, magnesium, calcium, strontium, barium, and radium have a charge of +2, and they do that because they want to lose both of their valence electrons. Now, skipping the transition metals here for a moment, boron and aluminum would have a charge of +3, and you can see it written there at the top right corner, +3 and +3. Same with gallium and indium, okay, in fact. And then it gets a little tricky with some of the transition metals, but yeah, they have charges of +3 because they have 3 valence electrons that they would like to give away, but they must give away all 3. It's an all or nothing deal. You can't have fluorine come along and only take 1 of them away. You're going to need, like if you're aluminum, you're going to need to combine with 3 fluorine atoms so that you can give away all 3 of your fluorine. You're not going to combine with just 1. Okay? You have, if you're going to give 3 electrons away, you must give them all completely away. So you have to find 3 fluorines to accept them then. Okay? All right. So let's get back to this. Here are some examples. So as we said, sodium. Sodium has 1 valence electron, and then it loses that valence electron, and now it has a charge of 1+. So now we write it like that. It's 1 valence electron with the plus sign means it's a positive charged cation. Okay, and that's it. Magnesium, though, has 2 valence electrons. It has to get rid of both of those, and when it does that, it's going to become Mg with a charge of 2+. Okay, and finally, aluminum has 3 valence electrons, and it has to lose all 3 to become aluminum 3+. So it's very important you understand what I'm doing, and you can just look at a periodic table and you can tell. Column 1 is 1+, column 2 is 3+, and then you skip over the transitions. You know, aluminum and boron would be 3+, okay, and so on. All right, so alkali metals have a +1 charge. Alkaline earths like magnesium have a +2. Aluminum have a +3. We talked about that. Okay. Now, sometimes transition metals come in more than one version. Now, this is a little weird. So for the transition metals, there's some, they have, we call them multivalent, which means like some iron atoms have 2 valence electrons, some have 3, and for reasons that are too complicated to get into in grade 9. Okay, but because there are 2 versions, I included that here in the periodic table. You'll notice that, like, if you look at iron, they write the 2 charges there, but that's a little hard to read. So what I did was on page 2 here, we wrote some of them down. Like, this is basically a list of most of the metals that you come across, and a few things that you don't really need to know in grade 9. But here, let's take a look at iron. Notice that iron comes in this version of iron with 2 valence electrons, okay? But iron also comes in this version with 3 valence electrons. So there's 2 versions of iron, iron 2 and iron 3. Notice how we use the Roman numerals to tell you which one we have. So look at the name of iron 2. We always use Roman numerals for that. So iron 2 versus iron 3. Now lead comes in 2 and 4. So here, actually, I stand corrected according to this. It's funny because some sheets I have different information. According to this, lead comes in 1+. Sometimes we don't write the 1, okay, if it's just 1. But lead also comes in 4+. It's 4 valence electrons. So we call these multivalent. Now, if I want you to write down the formula for a compound that includes any of those elements, I would use the Roman numerals to tell you which version of the element you have. Now, you would, let me put your mind at ease. You don't have to memorize these numbers or anything like that, unless you're ADA, of course. Okay, unless you're ADA. Because, I mean, there's no justice for ADA 2020, right? Maybe in 2021 there'll be some, but there's just none this year. I'm sorry, ADA. So the rest of you, though, do not have to memorize any of these values or any of these charges or anything like that. You're just going to have this periodic table. I printed a copy for everyone, so when you write your next quiz with this, you'll have all of this, okay, and the periodic table. So you'll know how to spell the names of other elements, including ones that I did not ask you to memorize, like bromine, iodine, and so on. Okay, so like now it's kind of different. You have the periodic table, so we can ask you more questions than maybe we would have just from your memory, right? All right, so getting back to how atoms combine. So transition metals, let's look at the iron that has 2 valence electrons. Well, that becomes Fe2+, and we call this iron 2. Okay, gold, if you're curious, let's go back. Gold is an interesting one. I was just reading an article, by the way, just since we're talking here. I was just reading an article about how gold, we're not sure where all the gold in the universe is coming from. As you know, supermassive stars can only fuse elements up to iron, okay, before they run out of energy for fusion. We think gold and heavier elements come from maybe collisions between neutron stars. So think of that next time you look at a gold piece of jewelry, that would have come from a neutron star, okay? A collision between 2 neutron stars. Anyway, I digress. So gold comes in +1, and gold also comes in, I believe, +3, yeah. So here's the other version of gold over here, 3+. Okay, so let's look at that. I'm just going to go back to our how atoms combine. So if I want to look at gold, let's do AU, pardon me, I almost wrote silver. That version of gold has 3, and it becomes AU3+, and we would call this gold, whoops, Roman numeral III, okay, gold 3. All right, good so far, right? So that's how cations form. Metals form cations. Nonmetals, on the other hand, like to take electrons to fill their outer shell and form anions in the process, okay? But again, when they do this, they must completely fill the outer shell. So for example, if you're oxygen, in order to have a full shell, again, we'll go back to the periodic table. Okay, so oxygen, like neon here, has a full shell. Oxygen is 2 electrons short of a full shell. It has 6 valence electrons, but it needs 2 more, okay, in order to get a full shell. So it must fill it. It can't just get 1 more and be like fluorine. That would make it more unstable, and that actually never happens. They never become more unstable. The goal of the atom is to become more stable, okay? So it needs 2 electrons. Oxygen here needs 2 electrons to become more stable, and it must get those 2. Okay? Let's get back to this. And fluorine, on the other hand, has 1, 2, 3, 4, 5, 6, 7 valence electrons. It needs 1 more, so it's got to gain an electron from somewhere. And so what it does is it finds a donor, often a metal, and you fill in the full shell. Now it has a charge of 1 minus, which means it's got a -1 charge because it gained a negative. Pardon me, I'm eating. So now it has a negative charge. Oxygen has 6 valence electrons. It has 2 empty spots. So to fill them, it's going to need 2 electrons. Now, we usually don't write the dots, like just to save ourselves writing the dots all the time. Usually the ion is just written like that. Same with this. We just write the element and the charge. Okay? So, generally speaking, when metals and nonmetals combine, it's a donor-receiver situation. What that means is metals will donate their valence electrons to the nonmetals, which receive them. And when they do that, they form ions, or ionic compounds. Okay? Now, table salt is probably the most familiar ionic compound, okay, for you. So I'm going to use that as my first reference here. But this is really cool. Like metals, ionic salts have high melting points. Now, I tried to do this in class. I tried to melt some salt with a blowtorch, okay? And I couldn't do it. The torch isn't hot enough. So like metal, the salt doesn't melt with high heat. Now, don't confuse melting with dissolving in water. That's not melting. That's dissolving. That's something very different. But the solid crystal has a very high melting and boiling point, okay? Now, unlike metals, though, they're brittle and not malleable, okay? So they're not malleable or ductile, and I'll explain why. Okay, remember why metals are malleable and ductile has to do with the sticky sea of electrons, like the Rice Krispie square? Well, they don't have the sticky sea here, okay? So I'll explain. They're poor conductors of electricity. Again, unlike metals. They're not good conductors in solid form. When they're dissolved in water, that's different. The solution, okay, can have good conductivity. They are usually soluble in water and form solutions. So like when you take salt and put it in water, the salt seems to disappear. What's happening is the water molecules can actually pull the ions out of the salt crystal, and now they're floating around and mixing evenly with the water, okay? So that is called a solution when that happens, right? They form network solids that are in a crystal form. So picture salt crystals, table salt crystals, okay? They can actually be quite large. We grind them up, obviously, to put on our food. All right, so here's the deal. Let's talk about table salt. Let's talk about good old friendly sodium chloride, okay? Sodium and chlorine by themselves are toxic, but when they're in the form of, when they combine and form table salt, they form an ionic compound, which is safe to eat. You could never eat individually, okay, a sodium metal, put it in your mouth, it'll, you know, create hydrogen gas, have a very sort of fierce chemical reaction with your mouth. okay, within your mouth. And chlorine gas will kill you. It's like a toxic gas. Okay, well, it'll kill you if it's concentrated enough at least. And so by themselves, these two elements are extremely dangerous. But when they combine to form ions, the two ions are extremely safe. Because you see, once sodium has already given up its electron, it's no longer dangerous. Okay, it's no longer explosive to put that ion in the water. Same thing with the chlorine. Once it gains its electron and becomes the chlorine anion, they're called chloride, it's also quite safe. Okay, so in their ionized forms, sodium and chlorine are perfectly safe. Now here's the deal. The sodium atom, when it loses its electron, so here the electron goes away, okay? Actually here, might as well put where it goes. Here's the electron going away. It's going to go join chlorine down here. Now when that happens, the atomic radius of sodium actually will decrease sharply as it sheds its outer valence shell. Okay, and the inner one is quite a bit smaller. Okay, it's kind of like neon now, right? So it has this full outer shell underneath. So now here's the deal. These purple guys, that's the sodium ion. Okay, sodium with the 1 plus next to it. Whoops. That's the sodium ion. Down here is the Cl1 minus ion. Okay, and when they combine to form a solid, okay, so this is like a solid. This here is a network where this is how they bond together and form the solid crystal that we think of when we see salt crystals. Okay, so what's happening is it's like 1 plus, 1 minus. They're alternating, right? So here you have a negative, then a plus, then a negative, then a plus. And then right next to that plus is a negative. And then another plus, and then a negative, and then a plus. Okay? And if you look closely at this, next to every negative is a positive charge. See, opposites attract, right? So opposite charges opposite charged ions attract by electrostatic, sorry, I need to write this a little better, attract by a force of electrostatic attraction. And this crystal then is held together with a pretty strong force, and therefore it's a high, I'm going to write high MP, high melting point, and high boiling point. Okay? So that crystal actually will have there's lots of force holding it together. Okay, now that's how these crystals form naturally. Okay, if you let them form. Now here's the deal. If you hit it with a hammer though, unlike a metal, it's not malleable. Okay, and there's a reason for that. Remember, metals are held together by a sea of negative charge that acts like a glue. Okay, the electrons are released, and it's the electron cloud that's sort of inside the metal that acts like a glue that sticks the positive metal ions in place. It holds them in place. Okay? Now if you were to hit, it's like the sticky sort of marshmallow in a Rice Krispie square, right? So if you hit a Rice Krispie square with a hammer, it doesn't break apart, it's not brittle. What happens is it's malleable instead, it flattens out. And that's because the sticky glue is still in between everything holding it together. Okay? Well, in the case of ionic salts, there's no sticky glue. They stick together because opposites attract, but if you were to take a hammer and let's say hit the hammer right there on the side of that crystal, it could push this side here, I'll color it in red, it could push this little group down. So if that whole group moves down one sort of atom, then instead of it being next to a neighbor that it attracts, it'll be next to one that repels it. So for example, positive charges repel other positive charges. So if I push up this positive charge here, let's say this guy, down one spot, so it's in this position, now what's going to happen is going to repel from that guy. Two negatives will also repel, so these guys will repel. And what will happen is the crystal will shatter. So it's quite brittle. Okay? It's not like the sticky glue of electrons that move freely in there. Here it's a rigid structure. There's no movement in it. except for the sort of vibrational movement due to like the kinetic molecular theory, right? But that's it, okay? So that explains these properties that you're seeing. Now, why are they soluble in water? Well, a water molecule is kind of a special molecule. We'll talk about water molecules a little bit later in this lesson. But water molecules, okay, look like H2O. So here's this thing that comes along. And the water molecules are special, okay? They have this special quality called polarity. And what they can do is they can pull the individual ions out of the crystal and make them sort of float around in the water. And so that's what happens when you pour salt into water, is the crystal dissolves as the water molecules pull the negative and positive ions out of their lattice work, and now they're dissolved in solution, okay, mixed evenly with the water. So we can see that ionic salts have these various properties that can be explained easily if you understand how negative and positive charges work, okay? Okay, now let's just finish this off by talking about how the ratios in which they combine. So ionic compounds will have to get together in specific ratios to make sure each atom gains or loses the correct amount of charge, okay? So you name them. The naming is really easy. You name the metal without changing its name. And you always list the metal first, okay, never the non-metal. But then you finish the non-metal, okay, you finish by naming it with the non-metal, but you change the ending to IDE. So fluorine becomes fluoride, chlorine becomes chloride, iodine becomes iodide, bromine becomes bromide, right? Phosphorus becomes phosphide, okay, sulfur becomes sulfide, oxygen, oxide, nitrogen, nitride, okay, carbon will become carbide. Get the idea? So you change the name to -IDE. So here's our examples. Sodium and chlorine, right? Sodium is 1 plus, chlorine is 1 minus. They're a 1-to-1 ratio because this guy has 1 electron to give. This guy wants 1 more. So they combine in a 1-to-1 fashion. But the name is just sodium chloride. Okay? Now, what about magnesium and fluorine? Well, here's the deal. Magnesium has 2 electrons to give away. Okay? Fluorine, though, only wants 1 electron. So how does that going to work? Well, you need 2 fluorines, okay? You'll need 2 of them. I gotta erase that. I'll circle them instead. I need this fluorine and this fluorine, okay? They're going to combine with 1 magnesium, okay? So that way the magnesium will still give away 2 electrons. It must give away 2 because it's magnesium. It has 2 to give away. Has to give them both away. And it'll combine with 2 fluorines to produce this compound you see here. So here that indicates we have 2 fluorines for every 1 magnesium. Okay? Now we don't write the ones. If there's no number written, the 1 is implied. Okay? Now how do we name it? Well, we just call it magnesium fluoride. So the naming is easy. Just name the metal and change the non-metal to end with IDE. All right then, let's talk about aluminum. Actually, I'm going to erase some of these arrows and stuff. Let's talk about aluminum and oxygen. Now I can go to the periodic table. I know aluminum has a +3 charge, so it has 3 electrons to give. But here's the weird thing, oxygen will only accept 2. So you have to find a way that these can combine so that it all balances out. So what you do is, if I take 2 aluminums, 2 of these guys, if I multiply that times 2, okay, I'll have 6 electrons to give away. And if I take 3 of these guys, that's also 6, okay? So as long as the charge balances out, I have 6 electrons here, 6 electrons here, 6 electrons for the oxygen. Now it's balanced, so they combine in a 2-to-3 ratio, 2 aluminums for every 3 oxygens. Now how do we name this? Aluminum oxide. Okay, so there's the 2 and the 3. That means how many of each atom you have. All right, let's do another example. Calcium has a charge of 2 plus. Oxygen has a charge of 2 minus. Okay? When they combine, it's 1 to 1, not 2 to 2. It's 1 to 1 because for every calcium that wants to give away 2 electrons, all you need is 1 oxygen, right? Okay, now the aluminum example points out something here. I'm going to point this out to you. There's a little trick. When it's kind of complicated, you can cross these numbers over. Okay? And that'll tell you how many of each one that you need. Okay, so let me show you how that works. Let's say we have a metal. Let's call the metal A. It's just any element, whatever it is. So here's A. It has a charge of X positives. Okay, and here's B. B has a charge of Y negatives. Okay, you can cross these numbers over, and this compound will be AYBX. Okay, that's called the crossover rule. I'll show you some examples in a moment. So that's the crossover rule. And you must put this in lowest terms though. So if, for example, okay, if A was 4 plus and B was 2 minus. Now that's not, these aren't 2 elements on the periodic table, I'm just making this up. 2 random like elements, who knows what they are, just call them A and B. You have to put this in lowest terms. So I'm not going to put a 4 and a 2 like this. What I'm going to do is those numbers are both divisible by 2. So I'm going to divide them both by 2 first. And I get, this will become a 2 and that'll become a 1. And so when they combine, you're going to get A, B, 2 like this. Okay, in lowest terms. So cross over the reduced terms. Okay, it's important to do that. All right, here's some examples. Okay, I'll just do a couple of examples. I picked this one on purpose, iron. Iron is one of our multivalent guys. So if we go back to the periodic table, remember that you always get this table. So iron is on the list, and if it's iron 3 plus, it has this charge, Fe3 plus. Okay. So now going back to how atoms combine, part 1. That's iron 3. And then sulfur, if you look on the periodic table, again, I'm going to show you like my thinking. So if I find, oops, I clicked on the wrong thing. Periodic table. If I look up sulfur, sulfur is a non-metal, so I go over here to my non-metals. There's sulfur right there. Well, argon has a full shell, so count backwards from there. It's -1, -2. Okay, so sulfur has a charge of -2. All right, so now back to here. So that's how I determine my charges. You can cross these numbers over, and I get Fe, it's already in lowest terms, S3, and this would be called iron. But I have to put the Roman numerals, iron 3, sulfide. Okay? So, there's an example of how you use the crossover rule. All right, so I could put more examples, but I think you get the idea. I have a worksheet for you. Here's your worksheet. I'm going to push this into everyone's folder. Okay, if I write the name of the compound, you need to write the formula. Okay, so let's do it together. I'll do one with you. Sodium and fluorine. Sodium is 1 plus. Fluorine is 1 minus, so they combine 1 to 1. All you have to do is write NaF. Whoops, it's capital F. NaF is sodium fluoride. Okay, let's do a hard one, or harder one at least. Let's do calcium phosphide. So calcium is 2 plus. Okay, that's calcium. Phosphorus is 3 minus. So cross them over, it's going to be Ca3P2. And that's pretty much the idea, okay? Now I did include some of these guys here at the bottom, notice that if it's a multivalent one, we have to tell you what the charge is. So here, cobalt 2 chloride, we know the cobalt is 2 plus. It tells me, so it makes it easy, right? Because it tells me. And here, this lead would be Pb4 plus, okay? Because IV means 4. Oxygen is -2 and chlorine is -1, so you can just look those up on the periodic table. Okay, now down here, you have to write the names. So this is super easy. You know, the first one here, lithium chloride, magnesium sulfide, just change the non-metal to IDE. That's all you have to do. It doesn't matter what the numbers are. So that would be zinc phosphide, right? This one would be sodium nitride, and so on. Okay, very straightforward. Now there is a trick with these multivalent guys though. The iron, the silver, the gold, and the nickel. Okay, what you have to do is you have to figure out what their charge was supposed to be. Okay, so let's do this one here together. Okay, what version of iron is that? Well, now we're going to do the reverse crossover. We're going to do it in reverse. So I'm going to take these numbers and put them back up to the charges. So in the reverse crossover, it must have been the 3 plus version of the iron, and then O is always 2 minus. Okay, so now looking at that, we can see that the name would be iron 3 oxide. Okay, so iron 3 oxide, if that should make sense to you. Okay, but these guys at the bottom that I wrote in by hand are multivalent. So what you're going to have to do is go back to the periodic table here, look on page 2, and then you can see what the possible charges are for the silver and gold and so on. Okay. All right. So that's how metals and nonmetals combine. They form ionic compounds. Now you know how to name them. You know how to write their chemical formula. Okay. So that's actually we're doing quite well so far. All right. This lesson though it's not quite done yet. I have to show you how other things combine. So let's go to this page here for a moment. Covalent compounds. Okay, so when nonmetals, I'm going to highlight this, nonmetals can combine with each other, but they don't form ions this time. Okay, so the only way they can really combine is not to give electrons away or take electrons from other nonmetals. What they do is instead they share them. And when they do that, they form a physical bond. Okay, so let's say I'm hydrogen and you're an oxygen. I would like 1 more electron and you would like 2 more oxygen. You would like 2 more electrons. Well, I could share my electron with you. And what we do, we'll sort of hold on to it together. So you put your hand on it, I put my hand on that electron, and it's kind of like a little tug of war between us, but neither one of us is going to let go. So now we're bonded together. Okay, like we're each trying to grab that electron, but we don't want to let it go. Okay, so we stick to it, and we stick to each other then. Okay, it's like if you're both fighting over your science textbooks, I'd say neither one wants to let it go, so you both hold on to it. Well, now you're bonded together, in this case with the electron, but in your case with the book, right? And I totally get how you would fight over your books, of course. Okay, so the key is they do not form ions. Okay, they do not form ions. Instead, they stick together to form molecules. So sometimes we call covalent compounds, which are made up of only nonmetals. Only nonmetals, okay? We call them molecular compounds because they form molecules. Okay, water molecule is a classic example. Okay, so we call them covalent compounds or molecular compounds because they form molecules. Okay, unlike ionic compounds, they do not combine with the crossover rule. So what we just learned about doing the crossover rule, you don't need that for this. Okay, in fact, they combine in several different combinations, and I'm just going to give you a few examples of that. Let's take our old favorite, water. Okay, water is a combination of hydrogen and oxygen, and it's in a ratio of 2 to 1. There's 2 hydrogens, there's 1 oxygen, right? So when the hydrogen shares its electron with the oxygen, they form a bond, a sharing bond, okay, and they stick together and form a molecule. Okay, and we draw the bonds with sticks. We call them stick diagrams. Okay, so here we see, I should finish that stick. We see that, you know, this is our oxygen here is the O, and the two H's, this H here and that H there, are bonded to it. Okay, well, here's my O. Okay, they're bonded to it by sharing their electrons. This way the oxygen is happy because it's sharing 2 electrons with the 2 individual hydrogens, and the hydrogen's happy because it has a full shell too, sharing an electron with the oxygen. Okay? Now that's one way that hydrogen and oxygen combine. Well, this is another way. Okay? That's called peroxide, the 2 oxygens and 2 hydrogens, H2O2. And that's another way that they bond together, okay, is with you know, a completely different arrangement. So this is a completely different molecule. This is the one they use to bleach your hair or whatever, okay, or clean a wound. It's kind of toxic, and so it can be used as an antiseptic, right? And it strips away dye from, or not dye, but pigmentation from your hair, okay, and that's why it can bleach your hair as well. All right, oxygen. Sometimes, here, let me do this. Sometimes an atom can share a pair of electrons with another identical atom. So those are 2 oxygens. This is O2, okay? It's a gas, okay, at room temperature. That's the stuff you breathe. Okay, you don't breathe individual oxygen atoms. You breathe you bear a pair of them in, okay? So they come in pairs, and they're sharing with each other to make each other more stable. Okay, so let's take this example of sulfur and oxygen. You can get many different compounds. That's called sulfur monoxide when you have just 1. This is sulfur dioxide when you have 2. This is sulfur trioxide when you have 3. And here we have disulfur trioxide. See, sulfur and oxygen can combine in several different combinations. There's no crossover rule to predict it. It's not like you say, all right, sulfur's -2, oxygen's -2, so they combine 1 to 1. Well, that's only one combination. That's only this one. They don't, all these other, well, what about these other ones? Well, they exist in nature, so like obviously the story is more complicated than you realize. So when they're sharing, they don't form ions, right? That's why the crossover rule doesn't really work. Carbon and fluorine can form various compounds also. You can get 4 carbons, or 4 fluorines, pardon me, binding to 1 carbon atom. We call that, that would be called carbon tetrafluoride. Tetra means 4. This would be dicarbon difluoride, and this time we don't put in those terms either, because there's actually 2 carbons and actually 2 fluorines in the same molecule. So we're telling you how many they have. This is carbon monoxide, so that's carbon and oxygen combining. And here's another way they combine, carbon dioxide, which you're probably familiar with, right? Carbon dioxide. Okay, so the deal is, because they have several different combinations, we name them by using prefixes, mono, di, tri, and so on. So mono means 1, di means 2, tri means 3. That's pretty easy. Just remember mono means 1, so students don't remember that. Tetra means 4, and then it gets easy after that. Penta means 5, hexa means 6, hepta 7, octa 8, nona means 9, and deca means 10, just like they do for polygons in math, right? A decagon is a 10-sided figure. So deca in chemistry means you have 10 atoms of something. Okay, and remember, you only name it this way. You only name it this way. You never name ionic compounds like this. Only the covalent compounds with non-metals only are named this way. So I put a few examples for you here. That one there is nitrogen dioxide, okay? And here, NO is nitrogen monoxide. So those of you who are writing no on the group chat, and you're writing nitrogen oxygen, that's unacceptable now. You now must write, if you want to say no in a chemical way, you have to say nitrogen monoxide. Otherwise, you're going to lose a mark, I have to say, okay? So we have to, you know, we have to get with the program, do it properly, So NO is really nitrogen monoxide. Okay, and we should name these things properly. Okay, and that's it. So what about this? Well, that is 2 phosphorus and 4 oxygen, so that would be called diphosphorus tetraoxide. Okay, 4 oxygens, 2 phosphorus. We still change the name to end in IDE. Notice that's always the case. Now, some things have special names. We're going to talk more about this tomorrow. Some things have special names. So that is the structural diagram for a carbon that's bonded to 4 hydrogens. So you can see there are 4 covalent bonds there, right? There's one here, there's one, like this is one here, okay? This is one here, that's one there. These are 4 covalent bonds, okay? And we could legitimately call this carbon tetrahydride, okay? But in fact, we have a special name for it, methane, okay? Another example of a hydrocarbon compound would be 2 carbons and 6 hydrogens. You could legitimately call it dicarbon hexahydride, but we have special name for it. We call it ethane, okay? 3 carbons surrounded by hydrogen would be called propane. 4 carbons surrounded by hydrogens would be called butane. And then after that, it's pentane, 5 carbons. Hexane, 6 carbons. Heptane, 7 carbons. Octane is gasoline, that's 8 carbons. Nonane would be 9 carbons, and decane for 10 carbons. So some things have special names, okay? And there's going to be a few special names that we're going to learn that are sort of the exception to the rule. But some things have more than one name. Like for example, here, if I write dihydrogen monoxide, okay, that, how many hydrogens do I have? Well, I have 2. That means 2. How many oxygens? Well, mono means 1. So this is H2O. Well, you know what the common name for that is. It's water. Okay. So some things have common names, we call them. So propane is what you use in your barbecue, okay, at home. So propane is, C3H8, okay, 3 carbons. You could call it tricarbon octahydride, but we just say propane, okay? So the hydrocarbons, I'm going to teach you that list of hydrocarbons because it's a very important list for your future. But for now, we'll just keep it simple. And I have a sheet for you here. Let me erase that. So this sheet has some rules. I'm going to tell you right now that you need to memorize these prefixes. Okay? So you have to memorize it. And remember, only covalent compounds. Don't name the ionic compounds like this. That's simpler. They have a different rule. Okay? So there's a couple of examples here. Diphosphorus Pentoxide. Okay? Di means 2. Penta means 5. So you've got 2 phosphoruses and 5 oxygens. Diphosphorus Pentoxide. Name the following compound. If you have one I and 7 Fs. Okay, 1 I and 7 Fs. You don't use mono. Okay, I'm going to just tell you. Mono means 1. But you don't use mono if the first element in the formula has only 1. The first element is an exception. You never call that mono. Okay? So if I have CO2, I don't say monocarbon dioxide. I just say carbon dioxide. So in other words, the mono is implied on the first one if you don't use it, if you say carbon something. If there's more than 1, though, you have to use di, tri, and so on. However, if the second one has only 1, then you use mono. So CO is carbon monoxide, okay, CO. Not monocarbon monoxide, you just say carbon monoxide. That means you only have one of the first one, too. Okay, so I'll do 2 of these for you, okay, and I'll take it from there. So SO2 would be sulfur, so you just name it. Whoops. Sulfur. And then it's dioxide. Right? One word. What about the next one? sulfur trioxide. Well, that would be SO3. 1 sulfur, 3 oxygens. Okay? Here, let's go down this guy, diphosphorus pentasulfide. Okay, you get the idea? So I'm going to push these worksheets into your homework. Please do it. If you look at other homework, it's not very long today. It's only one lesson. So hopefully you'll find that easier. And there's not a lot of homework moving forward. So if you look at the homework for today, do the worksheets, plural. Won't take long. I'd say it takes 15 minutes. Okay? And then there are some additional practice questions on those 2 pages. So please give those a shot. All right, that's it for today, guys. And we'll see you tomorrow.